Alright guys, in this video we're going to specifically cover everything you need to know for the homework in section 5.4, which deals with graphing rational functions. And in this homework it's going to tell you to use a 7-step process, which is what the textbook kind of uses. However, I'm going to break it down into what I like to call my 6-step process. It's the same process, it's just I do things in a little bit different order than the book does, and I kind of combine some stuff. So we have our 6-step process for graphing a rational function, and in this video I'm going to work through 5 examples. 5 examples of graphing rational functions manually. This is going to be kind of a lengthier video, but I assure you I'm picking all 5 examples for a reason. There is nothing in here that I'm doing just for the sake of killing it. These are all different in some aspect, which is why I'm covering 5 different examples of this. So step 1 is always going to be to factor the function, numerator and denominator, and find the implied domain. And just like in the last video, the implied domain is going to tell us either the location of the holes or the vertical asymptotes, which is what step 2 is. Once we reduce it, that allows us to identify holes and asymptotes. Then we'll determine the horizontal or oblique asymptotes, and we haven't covered that yet, the oblique, which is the slanted. I mentioned it in the last video. We haven't done how to figure that out yet. That's what we'll do one example of in this video. Then we'll find the intercepts of the function, which is going to be our X intercepts, Y intercepts, and we're going to plot some additional values between and beyond all the intercepts and the asymptotes. And once we've plotted all these extra points, then we'll use all the points that we plotted to graph the function. Okay, so let's just jump straight into an example. F of x equals 3 over x squared minus 4. We have a polynomial function on top, the constant 3, polynomial on the function on the bottom, x squared minus 4. Step 1 is factor the numerator and denominator, and then find the implied domain. X squared minus 4 factors to x plus 2 times x minus 2. Alright, so the implied domain would be, if we look at our excluded values, when we set x, we say x plus 2 cannot equal 0, we get x cannot equal negative 2, x minus 2 cannot equal 0, which gives us x cannot equal 2. So our graph is going to be an implied domain of negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. So our graph is going to be made up of 3 pieces that are broken up. And the top doesn't factor. And step 2 is, so here's our step 1, if you will. Step 2 is going to be to reduce the function to lowest terms, identify any holes or asymptotes. Well, this function does not reduce. We have no factors on top and on bottom that would cancel. Okay, so the fact that this does not reduce means x equals negative 2 and x equals positive 2. They are both vertical asymptotes. Okay, so at this point we're going to just automatically jump over and start creating our graph. So x equals negative 2, we're going to put a vertical asymptote. X equals positive 2, we're going to add a vertical asymptote. And we don't want to use a solid line, we're just going to use a dotted line. Okay, and that's just going to tell us that we're going to have this broken up into 3 graphs, 3 chunks, not 3 graphs, sorry, 3 chunks. And that's what our implied domain also told us. Alright, step 3 is going to be our horizontal asymptote. And if you remember from the last video, to find the horizontal asymptote, you compare the degree on top and the degree on the bottom. Now on the top, the degree is, there is no variable, so the degree is 0. And then on the bottom, the degree is 2. And when the degree on top is less than the degree on the bottom, the horizontal asymptote is at y equals 0. Okay, and that's just a rule that you have to have memorized. That's just a rule, those 3 cases you have to have memorized. So what that means is we can now come in here and y equals 0, which is our x-axis, we can draw a horizontal line. And so now we've got the starting of the graph. So we've got to have the detail of, okay, is this a rational function behavior over here going to look like this, or down here? It's going to be over here, or here, and in the middle, is it going to be like an S shape, or is it going to be like a parabola, one pointing up or a parabola pointing down? That's what we got to figure out. Okay, so the step 4 is going to be our intercepts. So, and let's just go ahead and figure out what the X intercepts are first. And to do that, we set the function equal to 0. And we're going to times the denominator over, and you always are going to do this process. So really, you don't really set the entire function equal to 0. You really just set the numerator to 0, because 0 times x squared minus 4 makes just 0. Now we get 0 equals 3. There's nothing to solve there. Okay, that's a equation that has no solution. What that means in context of this problem is there are no x-intercepts, which we should have knew that for the most part, because that was a possibility of that happening because of having a horizontal asymptote. Now, one thing that's important is the horizontal asymptote only applies to x as it approaches positive infinity and negative infinity. So it really only applies to the ends of the graph, which means that right here in the middle we could cross the x-axis, just not at the ends of the graph. So we'll talk about that more later with another example. But then to find the y-intercept, we're going to plug 0 into the function, and we get negative 3/4. Okay, so we're going to come in here and roughly at 0, negative 0.75, we're going to just estimate where that would be, and we're going to put a dot. So we've identified our vertical asymptotes, our horizontal asymptotes. We've got no x-intercepts, and we've found our y-intercepts. Now, we've still got to figure out how in the world do we draw this. Okay, and at this point, this isn't like a polynomial function where we can take advantage of, well, we know that these have to be connected in this manner. So on this, what we have to do is we have to just plot additional points. And we need to pick points that are beyond, between the zeros, the intercepts, and the asymptotes. So since we have an asymptote at negative 2, we need something that's beyond that. So for example, we need to plot a point out here at negative 3. That way we know the graph is either up here or down here. Now in between here, we've got the asymptote, the y-intercept, and then we have another asymptote. So we need a point in between all that. So we're going to also do negative 1. We're going to figure out where this point is. We're going to also do positive 1, figure out where this point is. And then we also need to know a value that's beyond the other asymptote at 2. So let's just do 3. You can pick any points you want. You could do negative 1.5 if you wanted to. Or you could do 478 for your value that's beyond 2. But we don't need to get crazy. We just need to pick values to get an idea of what's going on. And then to plot these, we need to know what their y values are. So we're going to plug each of these values into the function 3 over x squared minus 4. Okay, so f of negative 3 is going to be 3 over negative 3 squared minus 4. And guys, you can do this. That's 3 over 5. Right? So that's going to be plotted as the point, negative 3, 0.6. So I'm going to come over here to my graph. Negative 3, 0.6 is going to fall somewhere in here. And then we'll run through the same process with negative 1. 3 over negative 1 squared minus 4. That's going to, negative 1 squared is 1, minus 4 is negative 3. 3 divided by negative 3 is negative 1. We'll plot that point. Negative 1, negative 1. Same thing with 1. Same thing happens. 1 squared minus 4 is negative 3. 3 divided by negative 3 gives us f of 1 equals negative 1. So we're going to plot the point 1, negative 1. And what actually happens is this is an even function. It's even function, which means that it's going to have y-axis symmetry. So everything that happens here on the left is going to also happen on the right side of the y-axis. And when we draw that, we'll see it also. But then x equals 3. So that what that means is when we plug that in, we're going to get the same thing as negative 3, which gives us 3/5. So we're going to plot the point 3, 0.6, which would be roughly over here. Okay. And so what we know is we have to get extremely close to each of the vertical asymptote and the horizontal asymptote, but we can't cross them. So the fact that this point is here, and we have to get close to this line and this line without crossing them, means the graph has to look like this over here. And the same thing goes for this. We have to get really close to this asymptote, really close to this asymptote, but we can't cross them. Therefore, the graph has to look like this. And the fact that this is symmetrical means that we have to get really close to these two asymptotes without crossing them. So then the only logical way to connect these 3 points is for it to be a parabola. Okay? And so then if we go to Desmos, just do a quick check. Let's just run through and do a quick check of this. 3 over x squared minus 4. We do see that we get the graph similar to what we've created manually. Okay? And so, guys, take advantage of Desmos. Feel free to check your answers, make sure you're getting right, but realize that when it comes time to take an assessment, you have to be able to provide all the algebra that supports this picture. Okay? So it's very important to know how to do all these individual steps manually, and you'll be able to follow the process to get the picture. Desmos is a valuable resource to check yourself, though. It is a great tool for that. All right, and so now let's jump into give me just a second. Alright guys, and this is going to be the last one that we cover in this video. The next video I'm going to do is going to be, what do we do when the graph has a hole in the graph? What do we do when the graph has a slant asymptote? And what do we do if the graph doesn't have any vertical asymptote? So it's kind of like the video is going to be like rational functions, special cases, if you will. But this is going to be our last problem that we cover in this video. So f of x equals 3x squared minus 3x. So going just through this process. Step 1 is factor the numerator and the denominator. The top is a binomial, and we can take out the GCF 3x, and it factors to 3x times x minus 1. And the bottom is a trinomial, factors of 12 that make 1 are 4 and 3. And in order to make a negative, or a 1 with a negative 12, it would have to be a positive 4 and negative 3. So once we've factored it, we should see that the polynomial, or the rational function, I'm going back to this step process, guys. We're factoring to find the implied domain. So the implied domain is going to be x cannot equal negative 4, x cannot equal 3, which means it's negative infinity to negative 4, negative 4 to 3, 3 to infinity. So we see that once again this graph's going to have 3 pieces to it. Reduce it to lowest terms, identify the location of any holes or asymptotes. And we notice nothing cancels, nothing reduces. So that means that we're going to have any holes, we're going to have vertical asymptotes. At x equals negative 4 and at x equals 3. And just like in the last problem, I'm going to come over here and I'm going to start my picture. As soon as I realize that, 1, 2, 3, 4. I would not wait and try to find all the information first and then try to create the graph. Go ahead and create the graph as you're working through the problem. And I think it's less confusing, or at least it is for me. Alright, now we're going to find the horizontal asymptote. And so just like we said in the previous video and just like in the previous example, to do this we compare the degrees. The degree on top is 2. The degree on the bottom is also 2. And when the degrees match, the horizontal asymptote was always the leading coefficients divided. That was the rule that you had to have memorized. So in this case, the horizontal asymptote is going to be at 3 divided by 1, which means there's going to be a horizontal asymptote at 3. So I'm going to come over here and put a horizontal asymptote at 3. Alright, and that's finding our horizontal asymptotes. Now we're going to find our intercepts. Okay, so same process to find the x-intercept. We're going to set it equal to 0. And I'm going to go ahead and just use the factored form. Factored form is always going to be the easier to work with. And like I said in the last examples, on the last video also, we're going to times the bottom over. And 0 times anything makes 0. So really you just need to set the top equal to 0 when you're doing the x-intercepts. And then since this is already factored, we can split this up into 2 problems using the 0 product property. And we get that there's an x-intercept at 0 and there's an x-intercept at 1. So we're going to plot the points 0, 0 and 1, 0. Alright, now we need to figure out what's the y-intercept. And so to do that, we're going to plug 0 into the function. And we see that we get 0 over negative 12, which gives us 0. Which means we have a y-intercept at 0, 0. Which we should have known because we already had an x-intercept at 0, 0. Hopefully my computer doesn't die before this video is done. Alright, so let's just run through this a little bit quicker. That's not going to work. Alright, and the last part of this problem is going to be to plot test points. And so we need to pick points that are in between all of our zeros and our asymptotes and beyond. So we've got an asymptote at negative 3, so it means we need to check negative 4. We need to plot what's happening at negative 4. Let me just run through this real quick. F of negative 4. And for all these, I'm going to use the factored version. So 3 times negative 4, negative 4 minus 1, negative 4. Oh, sorry. That asymptote's at negative 4. So I need to use not negative 4. I need to use negative 5. Okay. Now I knew that was going to be an issue once I realized I was going to be dividing by 0. So let's plug in negative 5. So 3 times negative 5. Negative 5 minus 1. Negative 5 plus 4. Negative 5 minus 3. I'm plugging that into the factored form. So that's going to give me negative 15 times negative 6 on top, which is 90. On the bottom, I'm going to have negative 1 times, looks like negative 8, which makes 8. And then 90 divided by 8 is going to give me, 11.25. 11.25 roughly. Or not roughly, exactly. 11.25. Alright, so I'm not going to go, I guess we got room to. Go ahead, sure, why not? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So at negative 5, 1, 2, 3, 4, 11.25 going to be roughly here. And then guys, that's all that we really need for this part of the graph, because we know it has to approach each of these asymptotes without crossing it. So that's what that would have to look like. And I'm going to go ahead and come over here and do that vertical asymptote at 3. I'm going to go ahead and do x equals 4. So plugging 4 into it. 3 times 4, parentheses 4 minus 1, parentheses 4 plus 4, parentheses 4 minus 3. That's going to give us 12 times 3 on top, which is 36. On the bottom we have 8 times 1, which is 8. And then 36 divided by 8 is 4.5. And so 4, we're going to go up 1, 2, 3, 4.5. And once again, that's enough information for this end, because I have to get really close to the vertical asymptote, really close to the horizontal asymptote without touching it. So we know that's what that graph looks like. Now in the middle here, we've got a plot of point that's between and beyond all the zeros and the asymptotes. So we need to plot a point that's somewhere between negative 4 and 0, somewhere between 0 and 1, and somewhere between 1 and 3. So what we're going to do is we're going to plot 3 points in here. So somewhere between -4 and 0, I'm going to plot -2. So x equals -2. And then somewhere between 0 and 1, I'm going to plot 1/2. And then somewhere between 1 and 3, I'm going to plot 2. And then we're just going to run through this by plugging these all three into the functions. So f of -2, 3 times -2, -2 minus 1, -2 plus 4, -2 minus 3. Guys, you can work through this. That's -6. That's going to be -3. That makes 18 on top. That's 2. -2 plus 4 is 2. -2 minus 3 is -5. 2 times -5 is -10. So we get -1.8. So -2 gives us an answer of -1.8. We're going to plot that point. Okay, so we already know that this graph's going to do this. Now, 1/2. Same thing. 3 times 1/2. It's warning me. It's warning me. It's almost done. Going to pick up the pace just a little bit, guys. Alright, so here we go. Fractions. Everyone loves fractions, right? 3 times 1/2 is 3/2. 1/2 times -1 is -1/2. 3/2 times -1/2 is -3/4 on top. 1/2 plus 4 is 9/2. 1/2 minus 3 is -5/2. That makes the bottom -45 over 4. Now here's a convenient thing. Since the denominators are the same, that cancels. And then 3 and 45 reduced to 1/15. Okay, so 1/15 is going to be just a decimal that's slightly above 0. So at 1/2 we get 1/15. And then the last one we're going to do is 2. 3 times 2, 2 minus 1, 2 plus 4, 2 minus 3. So on the top we got 3 times 2 is 6, 2 minus 1 is 1, 6 times 1 is 6. On the bottom, 2 plus 4 is 6. 2 times -3 is -1. That multiplies to make -6, which makes -1. And then so we're going to come here and we're going to plot 2, -1. And so we see that the logical connection of all these is something like this. So then our final graph somewhat looks like what I have drawn here, guys. So anyways, we see this kind of a graph frequently with rational functions. I should have maybe covered one where there's an S shape in between, and I'll try to get that squeezed in the next video. But once again, we can go over here to Desmos and see that we do indeed get a graph that looks like what we have drawn manually on paper. Okay. All right. I'm going to stop this video here. There's going to be one more video for section 5.4, which is going to be graphing rational functions. In the last video, you're going to cover what do we do when we have holes, what do we do